September 24th, 1929, a turning point in aviation. Lieutenant Jimmy Doolittle had made the world's first successful blind landing. Flying a 15-mile course in a specially equipped plane without any view of the ground, Doolittle had landed completely by instruments and radio navigation. This is the cockpit that helped aviation first overcome the peril of fog. Until that moment, safe flying had been restricted to good weather. Today, pilots routinely bring their aircraft in for landings day or night in any kind of weather, even during heavy fog. They're guided by today's Instrument Landing System, ILS. This precise system is located at over 500 major airports throughout the world. For more than 30 years, ILS has been the international standard and will continue to meet aviation's needs in the future. Its long-proven reliability, especially at ideal locations, has earned this widespread acceptance. However, not all locations are ideal for ILS instrument landing systems.
It's 1441 Washington.
In some busy metropolitan areas, frequency congestion can be a problem because of the limited number of ILS channels.
Double 210, turn left exit.
ILS landings are restricted to a single narrow approach path, which can intensify noise levels for the community beneath the flight corridor. Another problem is signal interference, caused by reflections from nearby buildings, or airport structures, and even taxiing aircraft. In some locations, the most limiting aspect of ILS is the problem of the site. Terrain can impede the proper positioning of ILS components. ILS glide slope antenna must be set a specified number of feet to the side of the runway. To form a precise signal, it requires a minimum of 1,200 feet of flat, clear terrain in front of it. Initially, many small airports can only afford to prepare a minimum of land required for the strip itself. Later, when ILS service is desired, they must acquire additional land and fill in to create the level antenna site. Communities that decide to reshape their terrain discover it's a costly way to accommodate the ILS siting requirements. But with today's ILS landing system, it may be the only way for communities such as these to open their region to commerce, tourism, and industrial development. In other regions, there are mountains too large to move. And without an all-weather landing capability, the community's growth is indeed limited. Today's obstacles can be overcome by a new landing system. It's called the Microwave Landing System, or MLS. It gets its name from the part of the frequency spectrum that it uses. While the VHF, UHF bands of ILS have the capacity for only 40 channels, the microwave bands of MLS can easily accommodate 200. With MLS, the current problem of frequency congestion can be eliminated, and future landing systems can be assured discrete channels. With ILS, large antennas and large areas of clear terrain are needed to generate a precise guidance approach path with low frequency waves. The broad signal characteristics of these waves make ILS more susceptible to interference and signal reflections. Man-made structures such as hangars or natural objects such as mountains can cause reflections that distort the guidance signal received by the aircraft instruments. At many runways, removal of these obstacles requires costly site preparation, making ILS unfeasible. In contrast, the higher frequency microwaves are produced by smaller antennae. They form very narrow guidance beams that can be more easily controlled to overcome problems caused by obstacles. The conventional ILS is composed of a VHF localizer antenna, which provides fly left, fly right guidance information along the center line. A UHF glide slope antenna for fly up, fly down guidance information, and 2 marker beacons for discrete distance indications. Together, they form one single narrow approach path. All aircraft, regardless of size or approach speed, must line up, sometimes 10 to 15 miles away, to enter and fly this straight approach to the runway. Compare this with the MLS coverage. The azimuth antenna provides up to 60 degrees of precision guidance along either side of the runway centerline. The elevation antenna covers up to 30 degrees for varied glide slope angles, and distance measuring equipment provides range information throughout this entire coverage area. This precisely coded volume of airspace permits a wide range of flexible approach paths. Flexibility now impossible with ILS. This range of MLS glide slope angles will permit all aircraft to make approaches tailored to their own flight characteristics. Helicopters and short takeoff and landing planes can use the very steep angles within the range of MLS, while airliners can take segmented approaches, flying longer at higher altitudes over noise-sensitive areas, and then closer to the runway, make their more gradual final approach. The broad azimuth coverage of MLS can be used to guide aircraft along curving, winding river approaches, another way to avoid noise-sensitive areas. So you see, the microwave landing system will increase airport capacity in all weather conditions, while maintaining the airport as a good neighbor. There are several forms of MLS, but Time Reference Scanning Beam, or TRSB, is the one MLS technique which accomplishes this best. TRSB works this way. A narrow microwave beam generated by the azimuth antenna scans rapidly to and fro through the entire coverage volume. Another beam generated by the elevation antenna scans down and then up. When an aircraft enters this broad coverage volume, its receiver detects 2 pulses from each complete beam scan, from each antenna in the system. In the elevation, for example, the first scan sweeps down. As it passes the aircraft, a pulse is received and a timer is started. When the scan returns, a second pulse is received and the timer is stopped. This is the key feature of TRSB. Instruments in the aircraft derive the airplane's precise position from the time lapse between the 2 scan pulses of each beam. The aircraft position is updated right in the cockpit several times per second. Because TRSB generates each of these scanning beams at precise times, MLS onboard receivers can distinguish between direct and reflected signals. If the azimuth beam begins its 2 scan and is reflected by an obstacle, it will send a pulse out of time sequence, and the aircraft receiver will reject it. But as the direct signal passes the aircraft at the expected time, the receiver will accept the pulse and start the timer. Similarly, the receiver will reject all other pulses until the proper time interval is passed, and the direct fro scan is received. This simple but precise TRSB technique performs with the same high degree of precision in several different configurations. A compact system is available at minimum cost to meet the modest needs of the small community and general aviation facilities with Category 1 landings. Growing airports can begin with basic approach, azimuth, and elevation antennas that provide Category 2 guidance. And as required, they can add a second elevation for flare guidance in 0-0 visibility and a back azimuth to handle missed approaches. With suitable modifications, the same system can even provide 360-degree coverage. Time Reference Scanning Beam MLS meets every requirement for the all-weather approach and landing system of the future. More significantly, TRSB meets these requirements with a high-integrity system, one so inherently simple that it is flexible, modular, and at the same time requires the lowest cost avionics of all MLS systems. TRSB, the system here and now, suited to serve the world aviation community well into the 21st century. An ambitious claim, but one well justified in light of conclusive tests conducted at the Experimental Center of the Federal Aviation Administration. Here at NAFEC, experts from the National Aeronautics and Space Administration, FAA, the Department of Defense, and industry have been evaluating and comparing a number of MLS systems. Much of the work has been performed in NASA's unique 737. This flying electronic laboratory contains advanced airborne systems for a variety of experimental projects, one of which is to test the MLS time reference scanning beam technique. Within the aircraft, a second cockpit has been built to create an environment much like the hood of Jimmy Doolittle's plane. Crew members seated here can see nothing outside. They rely solely on their instruments and TRSB to land. The crew in the forward cockpit monitors the test flight, assuring safety. Specialists aboard the aircraft are in constant voice communication with the FAA ground-based range control.
Copy and move eyes when we're tracking.
Here, while the flight is in progress, the test data is collected and recorded. Data is automatically processed, and the flight pattern is plotted.
515 range.
The results on the board and on the tapes are later compared with the telemetric data transmitted from the aircraft in real time. When the aircraft enters the coverage area of TRSB, the pilot receives confirmation that the valid signal is being processed. He engages the automatic landing system. The plane begins its descent, guided by onboard avionics, utilizing the MLS signal. Range control monitors and records the aircraft's progress as it flies through approach to a flawless landing. The precise guidance signals generated by this elevation antenna and this azimuth antenna have proven their high level of integrity throughout hundreds of recorded flight tests.
And run 1, 2 coming up.
And the tests continue, flying different angles and different approaches. S-turns, 130-degree turns, and fully automatic landings. Each one is conducted, recorded, and evaluated by sophisticated electronic equipment and exacting technicians.
13, maintain 2.
And not only with this elaborately equipped 737, but with different types of aircraft, both civil and military, an Air Force T-39, a DC-6, and an Army helicopter. Through these tests, the TRSB system has proven its capability to span the entire range of approach and landing operations for all aircraft types, including short takeoff and landing aircraft. The same basic ground equipment can be adapted to special military applications, such as transportable or shipboard situations. And the same precise signal is received by low-cost avionics, completely compatible in both military and civil configurations.